Yes, go ahead.
All right, Ananda, are you there?
হ্যাঁ হ্যাঁ বলো।
All right, I'll go and so I'll be before I start, I'll be muting it. I'll be letting everyone know so that if someone joins in, then I don't hear the pinging. Okay. So hello everyone. We begin this year with the establishment of the Vanguard. I'm Saurabh, finishing up my PhD in ESPCI Paris. But it does not matter who I am or where I'm from. What matters is who we are and what we represent. We support open access, free for all, and we promote frugal science, cheap, quick, and dirty experiments that can be done by anyone, anywhere, anytime to obtain substantial research output. We are here to provide people without physical and social capital access and means of production, means to produce research. And it's not me alone, it's me and Broto Chakraborty, Shoikot Basu, Shoikot Mukherjee, and Saurabh Sarkar. So I'm from ESPCI Paris. Broto is doing his postdoc in NYU. Uh, Shoikot Basu is an assistant professor at South Dakota University, and Shoikot Mukherjee is also doing his postdoc in University of Minnesota, and Saurabh Sarkar is an assistant professor in Jadavpur University. The first step in line with the Vanguard that we have made along these lines is to give a series of lectures which will be available to all. And this would be the first lecture of that series. So I would be covering capillarity and elasticity. Brododa would be covering active matter. Shoikota would be covering biomedical fluidics, and Shoikot would be covering pattern formation. Today is the first lecture on capillarity and elasticity. So with that introduction and our manifesto, we start the lecture one, everyday physics, scaling laws. So let me first explain what I mean by everyday physics. It is the physics of what we see all around us, the mundane. But the subtlety in the mundane, or the extraordinary physics that lies in the ordinary. For instance, when you see a droplet of water hitting a dosa plate, what happens then? Or a raindrop sticking to your window pane, or perhaps wrinkles on your finger. I'll try to give this lecture in a very introductory fashion, so it will be pretty loose and it'll be general so that I can show you different kinds of phenomena that emerge out of this melting of different kinds of physical concepts. And what I mean by scaling laws is something uh, which is quite, to put it very loosely, instead of going into the nuances and subtleties of every phenomena, how to look at it broadly and how to make a poor man's model, a first order approximation, so to speak. I think it'd be better if I give examples instead of uh, wording it with different kinds of verbose, articulate, fanciful words. Uh, so let's go. So here you see raindrops sliding down a window pane. This is something that we have seen all our lives. This is the regular surface. And that's why you see some droplets are stuck. A solid surface is actually full of asperities. That's why droplets can pin on them. And this is exactly what we see here. But if the droplet is fast enough, it can move. The reason why these droplets stuck on the surfaces is not only the pinning, but also adhesion. And regular surfaces have a lot of adhesion. But not all surfaces are like this. There are some surfaces which are anything but this. For example, here you see droplets impacting on a super hydrophobic surface. And what you see is that they're bouncing. They gently deform and they rebound. Some deform more, some deform less. But how do you make such a surface? Well, let me show you quick and dirty way of doing that. Ooh. All right. So this is a candle. Now it's a lit candle. We will use this. It's something very general. This is a steel plate. If you put a drop of water on this, as you can see, if you can see, it's sticking to it with a very low contact angle. But I can turn this surface into a super hydrophobic in a very cheap and dirty way. One way to do that is just create coal or soot. So what I'm doing here is that the flame is going to make carbon deposits or soot particles will deposit on this plate, and you'll find this. And if I were to put a drop of water on this, did you see it bounces? I hope that.
Yeah, we can see. Nath, if I may interrupt, there is someone commenting that they cannot hear the audio. So could
What?
anyone else respond if they can hear us?
Yes, I think his audio is pretty good.
All right.
Okay, so go ahead.
So could you see that there is, so I wanted to show you, demonstrate that there is a droplet, which is pretty spherical. So when you deposit a drop on this, I don't know if it's visible, it clearly bounces. And these are all sticking on this side. That's because this is the adhesive part, but this is not. So I hope some of it was visible. And it's very cheap and dirty. This can be done at any point of time. It's not very robust. If you want something robust, then you take this. This has a nanoparticle coating on top of it. I got this from the lab of Ranjan Ganguly. And if you put a droplet on it, you can see that right here, they're sitting and they are quite spherical, like a pearl drop. Do you see it? All right. So now that we have established that, we can go back to where we were. Before we proceed any further, I think it's important that I establish what is the capillary length. Now there are different ways of doing this. I can write down a bunch of equations and also establish what is the capillary length by non-dimensionalizing it. But I think it's far more helpful and easier to visualize if I show you a very simple experiment to explain the concept. So here is a super hydrophobic surface, which is not necessary, but it's just here for ease of demonstration. And this we are depositing droplets of larger and larger volumes. As you can see, the droplet of the smallest volume is very spherical, but as you increase the volume, you see that it loses sphericity. In fact, the limiting case of this would be you take a glass of water and you just pour it on the ground. And it would not be spherical. It would be very, very flat. That would be the exact opposite of a very, very small drop. The smallest droplet here is 4 microliters. And the largest one is around 100 microliters. And we can see that the 4 microliter one is very spherical. So what we can do is we can extract some data out of this. This is an experiment that Choyun and I did 2 days ago. And if I were to plot the height versus the volume, you see that the height increases with the volume at low volumes, and then it gradually saturates. And what is this particular length at which it saturates? That's close to 3 millimeters. Now let's try to rationalize what's happening here. Clearly, there is a transition which happens with volume, and it becomes a puddle, a flattened shape, which means gravity, which is much more effective when it's larger, flattens it. And capillarity or surface tension wants it to be spherical, which is dominant at low volumes. So let's try to write this down in a scaling fashion. So if there's a drop which has a radius r, and its general sizes are, the surface energy would be gamma r squared. It would not be exactly gamma r squared. There would be a prefactor because we are not taking into account the prefactors here. So in a scaling way, I can just write gamma r squared. And if this surface energy is dominant over the gravitational energy, which is mgh, then I should see it as a spherical cap, as a spherical drop. But what is m? M is essentially rho r cubed, and the height of the center of mass scales as r. So if I plug those in, this essentially becomes, and if I cancel some terms from the left and right, I get the critical radius has to be less than the square root of density times gravity divided by surface tension. This particular length scale is that curious length below which capillarity is dominant, above which gravity is dominant. And if you plug in the values of density and gravity and surface tension, then what you see is you get 2.7 millimeters. There's that magical length below which you see gravity is invisible. It's essentially capillarity. You take a capillary tube, you dip it, it rises. You take a leaf, you tear it open, you see the veins of the leaf. They're all below 2.7 millimeters. They're everywhere. These are the capillaries. So now we can go back to this video again and observe something very curious. We see that all the droplets are bouncing on this super hydrophobic surface. But I can also extract data from this video. And if I were to extract data from this video and plot the contact time, the duration for which the droplet remains in contact with the surface, with the velocity for the same radius, I find a curious thing. I find that the contact time is constant. It is independent of velocity. That's an experimental fact, which was observed for the first time in 2002. Now, I would naively expect the contact time to be a function of not only the velocity, but also the material properties like density and surface tension and viscosity. What are the observations that we can make by just looking at this experimental plot? The first thing we note is that if the contact time is independent of velocity, that means dissipation plays no role, because viscous dissipation would have velocity changing, like increasing velocity would increase dissipation, but that has no effect. So viscosity has no effect at all. But what is curious here is that even velocity does not have any effect independently, which means even inertia has no effect. It's curious. The next observation we make is that the contact time is plotted with the radius for the same velocity increases with the radius to the power 3 halves. This is also very curious. This means that actually the contact time is dependent on the size, but not the velocity. Now, this tempts us to wonder what is a system where the contact time is independent of inertia, but a function of its size. It tempts us to think that it's almost like a characteristic time of this system, as if it were like a spring. Can we dare say it's a spring? Let's see. So this is the deformed drop, so to speak, and here, for instance, this would be the completed profile of the spherical drop, but it deformed at the bottom because the black line, which represents the ground, let's call this slight deformation delta. So I'm tempted to say that the force is gamma delta, where delta is a slight deformation I make, and it's like a spring. And maybe here we are completely wrong, but it's tempting to think that it's like a spring, because we know that springs, it doesn't matter at which velocity you hit it, the time period is essentially the same. It depends on the mass. And this force looks like a spring. The gamma is like the spring constant k, and delta is the x, the deformation. So time period would be the square root of m over k, as we have for a spring. And if I plug in rho r cubed for m, then we see that the time period goes as the radius to the power 3 halves, which is precisely what we saw. Of course, there are other complications, but to the first order, we see that all these rebounding drops on superhydrophobic surfaces are actually just simple springs. Hmm. But why is it important? You may ask. It's important because if you deposit a droplet on any regular surface, it would just stick, or it would splash if it's at a very high speed, as you must have noticed. But on these surfaces, like lotus leaves or this soot particles, as you saw, or surfaces with nanoparticles on them, which are super hydrophobic, the droplets rebound. It took 10 years to find out that this contact time, which was found out to be the least amount of contact time before it bounces, can actually be beaten by a lesser value. Let me demonstrate that. So here, on top, you have a super hydrophobic surface and a droplet is going to impinge on it. The right-hand side shows you the side view. On the left-hand side, you see the top view. And the bottom, you see the same surface, but with it's like a blade. It's like a 100 micron bead, 100 micron fiber on it. So you can imagine to be the edge of a blade. And if I play the video, the first thing we notice is that it took 7.8 milliseconds for it to rebound on this surface with the defect, which is the fiber, or which is substantially less than the time taken on the super hydrophobic surface. Let me play the video again to help you explain what I mean by this. So here it impinges, and after that, this is where it has rebounded from the one with microstructure, which is this fiber. It has still not rebounded from the super hydrophobic surface, and now it has. So immediately, then this is shown like 11 years later, and it was a very important study because we want to reduce the contact time for a variety of reasons and applications. While some people might not be interested in applications, but here is a very cool and important application. For instance, here is a molten tin drop. On the left-hand side, you see the control surface, which is super hydrophobic. And it's stuck on the left-hand side. On the right-hand side, it is rebounded all together. It's stuck because there's heat transfer going on, and it is going to solidify. So you want to rebound before you solidify. So you want to minimize the amount of time for which it is in contact with the surface. So it is very critical to minimize it. And up until now, we knew that the minimum time to rebound is by creating a super hydrophobic surface, which is corresponding to the characteristic time of it being a spring, the drop being a spring, which is square root of m over k, or rho r cubed over gamma. But it seems to not be the lowest one. You can beat it. But how? Why? How can you? What's going on here? Now, if you go back and if our arguments on the spring, which were very simple and naive arguments, they were true, then perhaps by looking at these videos carefully, we can understand them. This was shown by James Bird and Kripa Varanasi, and these set of experiments were done by Anais Cotier. On the left-hand side, you see a droplet impinging on a super hydrophobic surface with a 100 micron wire, and you see that it deforms into what looks like two lobes. At a higher speed, much higher velocity, you see that it deforms and it now becomes 4. Now we have a completely different geometry. It's a Y structure, and if you impinge the droplet, it becomes 3 lobes. So if our arguments were correct, then the contact time of these should not correspond to square root of m over k, because you have reorganized the mass and they are kind of independent. So corresponding to lobes, they should be square root of m over 2 over k. And it would be m over 4 for the second one and m over 3 over here, which corresponds to a decrease in the contact time by square root of 2 or square root of 3. Is it this? Because that would imply that the constant line of contact time versus velocity, at least for these two, if we were to plot this, because here we see that with higher velocity, it makes 4 lobes. It would not be constant, be constant and jump to a decreased time and remain constant and then jump again to a different value. It would be discontinuous. Is it really this? There you go. The black triangles show you the contact time on a just regular superhydrophobic surface, but the red data points are ones on a superhydrophobic surface with a thin microfiber and impinging on it. At very low speeds, you see that it's just impinging on the fiber; it doesn't even feel it. But at higher speeds, it deforms in two lobes, and there you see this is a square root of 2, a factor of square root of 2, the second level, and then it's almost quantized to another level, which is a factor of 2. That means our very simple argument of these droplets being a spring are not entirely wrong. They have at least some merit to it. So now we can move on to a dosa plate, something that you have definitely seen. You probably have seen people like the shopkeeper or the person who is making the dosa drop waters on, not with a micropipette perhaps, but just throwing water droplets. And what we see here is that these droplets are very mobile. They hover on these surfaces. Why? Well, the reason is that when the droplet comes close to this surface, the surface is so hot that it starts evaporating, and it then sits on its own vapor film. So it never comes in contact with the solid. So that is why, again, it's almost like a super hydrophobic surface. It's very mobile, and it moves randomly in any direction, if you notice that. So for long, this was first noticed by Leidenfrost in the 1700s, perhaps 1756. Maybe I'm wrong. And now a lot of work has been done on this because it also serves as a surface which is kind of water repellent. But what's interesting is that on these surfaces, if you've noticed in this video, the droplets just move in any random direction. And it was assumed for long that these droplets just move in any random direction because it depends on, I don't know, the asperities on the solid surface. It's not perfectly flat, and there's always, tiny bumps, and it's sensitive to it. Is it? So my friend Om, she did an experiment. This is the top view. On the left-hand side, you will see trajectories of the droplet when it is deposited with a radius of 2 millimeters. On the right-hand side, you will see droplets deposited with a radius of 1 millimeter. And this surface is as flat as it can be. I think around 0.1 radian is its tilt error or something. And this is what happens. We note that on the left-hand side, where the radius is larger, it's 2 millimeters, they're all going in the same direction. While on the right-hand side, it's just random. So suddenly there is a selection, there's a preference, there's a bias. The biased regime is for larger drops. Why? What suddenly happened? So let's visualize what's going on. So let's put some tracers in this drop. And so this is the experimental setup. On the bottom, you have a very, very hot surface, around 350 degrees Celsius. From the needle, you have a water droplet, which is, and this drop is millimetric, and it has some particles in it. Now, you'll notice that the moment I play the video, it is rolling. It has still not come in contact, but it's rolling. When you just dangle a drop from a needle, it doesn't roll like this. But just because it is in the vicinity of the hot plate, it is rolling. And when it detaches, it starts moving. So that begs the question, why was it rolling? Because that rolling clearly contributes to its directionality in some sense. Well, what we definitely can say is that if you go back here and play the video again, what we can say is that this is hotter than the top. And while you might think, oh, it's hotter, so maybe it has lesser density and all, but the real reason here is that because it's hot, so its surface tension is low, and because here it's colder, its surface tension is higher. So from lower surface tension, there's a flow going towards the higher surface tension, which is called the Marangoni flow, which happens along the surface. And this flow along the surface creates a circulation, and that circulation creates this rolling motion inside the drop. Okay, this can be proven also with other things, but this still does not explain why there is a selection of directionality that we have not done yet. For that, we need to take a large drop. Let's take a large drop. Let's put these particles inside it. But we don't want this drop to move, so we'll take a bowl. concave shaped. We'll take a sapphire bowl, quite expensive, not very frugal, but if you use this surface and you heat it up and you put a drop on it, then it's not going to move because it's like a bowl. It's going to sit in the middle. Then you can see what's going on it from the top. This is exactly what you see here. This is a top view of a droplet of radius 2 mm, which is the large drop, which is showing you the bias, which is preference in one direction. And now when I play the video, you see that there's a lot of things going on. There's a lot of motion happening. There are clearly cells inside, which are very visible. And they're also interchanging and they're moving very fast. Perhaps if I stop it at any point of time, I can see how many there are. It seems like there are about 4 of these. And let's just watch this video as the drop evaporates, because it's hot. So the drop is not going to stay in the same size forever. It's evaporating. And as it keeps evaporating, you see that the cells, they try to accommodate and reorganize themselves somehow, accommodating themselves inside the volume. But as the volume shrinks, the motion becomes slower and slower, and the droplet is now confused. It does not know what to do with the cells. The cells don't know what they're doing. It can't accommodate the cells. So they have their meeting and they discuss and then decide, okay, we will just move in only one direction. There you go. So suddenly this drop is now moving in only one direction. There's only one cell inside it. And look at the speed at which it is moving. So what happened? So clearly, so if you put a laser sheet inside this, then you can visualize this better. And here from the left to the right, we see an increase in radius. On the left-hand side, you see the smaller radius, 1 mm. And you see that there is one cell, one circulation cell inside, which we saw at the end of the previous video. On the right-hand side, you see 2, actually there are 4, because it's big, and they're counter-rotating. And there's this critical radius in the middle where this happens. What is this radius? This is again that radius from where you see the transformation from a spherical cap to the bottle. This is the capillary length. And this capillary length is the length beyond which, because it's not spherical anymore, it cannot accommodate one cell. It has to accommodate like 4 cells. So now, because there's counter-rotating cells inside it, so it's balanced. So it has no preference. So it feels the very slight tilt of the surface. So the larger drop feels the slight tilt, whatever there is, and they all go in the same direction. But the smaller drops, they are rolling in one direction, and this direction is arbitrary, and they just shoot in different directions. And that's why you see multiple trajectories. The symmetry breaking happens at the capillary length. So now that I've introduced you to the capillary length, perhaps I should introduce you to another kind of length, which is, well, before I tell you what length it is, let me explain what you see here. You have a very thin sheet, like a polythene sheet, very thin, say about 10 microns or less. And there's a water drop, which we are going to deposit in it. And let's see what happens. The moment you deposit the water drop, we see that the sheet wraps the water droplet completely. So can we try to predict what is the scale of this, or the size of this sheet below which we can see this effect? Clearly, capillarity was pulling on the sheet, and the sheet responded. It was balancing between its bending and capillary energy. Well, we can do some homework assignments from our undergrad mechanical engineering class. So we can take a sheet and we can look at the deflection that you have when you have a load. And while I'm not going to derive it here, but we know that delta goes as the force times length of the sheet cubed divided by the elastic modulus times the moment of inertia. Now, here, in this case, the force is gamma times L. Of course, it's distributed all along the perimeter. It's not only at the center, but it has the same form, the solution. And here the inertia I would be h cubed times L, h being the thickness of the sheet. So this would give us, if we plug this in, this would give us the extent to which it would deflect or move up. But of course, it would only be able to wrap it completely if delta scales as L. That's when you see a complete wrapping. So if we plug all of these in, then we can find out this critical L. And this L is the elastocapillary length, where both elasticity and capillarity are equally important. And this goes as square root of EH cubed divided by gamma, which is also called B over gamma, where B is the bending modulus. Uh, it's important to realize that when we compared capillarity and gravity, we got the capillary length, and here we got the elastocapillary length. You can also compare elasticity and gravity, and that's not something I'm going to do this time, but it is possible to consider a sheet of paper. You hold it in your hand, and imagine it being longer and longer, and at some point it's going to start to flop. What is that length? That would be the elastogravity length, and you can also determine it experimentally, and then you can find out how to rationalize it and what the value is going to be. These are the scales I'm talking about. But now in this case, the elastogravity length is a length where if you are less than this value, then capillarity is dominant. If you're more than this value, you'll see this wrapping thing happening. If you're more, let's see what happens. So this is what happens when you are less. This is a small, tiny shape around a few millimeters. And you can see when you deposit a drop, it wraps it. It was done by, so this entire thing of elastocavity was done by Jose Vico and Benoit Homa. They did seminal work on this. And later on after that, there were also others. The interesting thing here is that if the size of this sheet is much greater than this, then you see something very different. You see wrinkles forming. Now, while I'm not going to go into the details of how to explain the wrinkles, but I can show you practically how you can see the wrinkles. These wrinkles are not specific to just this phenomena. Yeah. So this is a thin plastic sheet, like any polythene. And if I pull it, see what happens. I don't know if it's visible, but there are thin wrinkles on it. Are they visible?
Yes, they are visible.
I can see at least 3 wrinkles. It's the same kind of wrinkles, but radially outwards. So perhaps in a later lecture, we can discuss more about how they happen. All right, so now, the very curious thing is that when you apply gel or even water to your hair and it sticks, and if you use the right kind of gel, you can just have these very elongated hair structures and fashion for you guys. This is also something which is just, if you take 2 fibers and dip it in water and the water rises up the fibers and it bends and you can see elastocapillarity. Again, just to let you know that this exists. And now we'll move on from elastocapillary length to something else. So now we are close to coffee stains, something that you have definitely seen all over your table and many other places. Like my table is full of coffee stains. So I'll give a very simple understanding of how coffee stains happen. It's something which is a very regular and mundane phenomena, but it encapsulates something which is also not very non-trivial once you know it. So evaporation is dictated by the equation, the diffusion equation, and the flux goes, which is the spatial derivative of concentration, dc dx. The flux always blows up in the corner. It's like the same thing when you have an electrical conductor where it blows up at the very pointy tip. Here, in this case, on the top what you see is that the evaporation would be much more near the contact line, and hence the amount it would recede would be much more than how much it would be at the top. And that is because, as I said, the flux blows up near the contact line. However, if there is spinning on any surface, in the very beginning video that I showed you of raindrops on a window pane, you saw that some of them were stuck. And if there is spinning, then what would happen is that it would start evaporating from the top, and it's coming down, but the contact line is not moving. So the arrow on the top schematic that you see, which was supposed to happen, that is prevented. So there has to be a compensating flow because it's evaporating from the top, and this compensating flow is what you do see when you observe under a microscope. These are 10 micron beads, and you see them collect near a contact line. This is exactly what happens every time you have a coffee stain. Not only coffee stains. This is also exactly what you see when you have aloo bhaja, because all your fries, you probably have seen, they are burnt near the edges. It's the same thing, because if you have corners, then these fluxes are going to diverge, and it's going to be fried more near the edges. In this case, there is no such particle motion happening through the fluid, but you have the same arguments regarding the blowing up of the flux near a corner. This gives us the perfect segue to the last thing that I'm going to show you, because I told you that I'm going to talk about at least rain and some coffee stain and some whiskey. So let's talk about some whiskey. So this is an experiment. Here, what we are seeing is this is a bowl full of oil, olive oil, for instance, and what you have in this what looks like an ink dropper is actually 70% alcohol with 30% water. So you can take some absinthe and add a little bit of water in it, and then put some blue dye, and then you take this and you deposit just one small tiny drop. And the moment you drop it, you see that it starts to break up into droplets from its rim. And you see that it keeps receding while breaking up into droplets from its rim. It keeps going on, going on, going on, and then it ends up at a point. And we have a myriad of droplets. So this is slightly more complex phenomena than before. Let me try to explain it, at least conceptually, what is going on here. So this is, the yellow part is the oil. And as you see that the thinner region is at the very extreme, at the thinner region, the evaporation will be much more. If the evaporation is more, that means alcohol content over there will be low. If alcohol content is low, surface tension of alcohol is lower than that of water. So then surface tension will be higher over there, because low alcohol means high content of water, so higher surface tension. While at the center you have a higher concentration of alcohol, which means a lower surface tension. That means there is going to be a flow from the center outwards continuously. This flow is going to collect at the very edge in the rim, which is going to disintegrate. Let's see. So this is the region where I said there'll be more alcohol, because evaporation is happening much more at the edge. And this is the region where you have less alcohol. And this tells us surface tension in the center is going to be lower, which drives the flow outwards, radially outwards. This constant flow is going to collect as a thick rim, and the rim is going to destabilize. This breaking up of this rim is not very different from the breaking up of the rim you see on a window ledge when it's raining. When the window ledge has a thin rim which keeps collecting water more and more and starts dripping, it's the same thing. So I'll play this video once more. We are probably somewhere here. And there you go. You see this continuous ejection of droplets. There are two instabilities here, which I'll talk to you about next time. And with that, we have moved from water to coffee, to some fried fries, to some alcohol. So we have had, if not a four-course meal, some kind of a meal with a lot of beverages. And with that, I'll say solidarity. Thank you. The idea of this particular introductory lecture was essentially to tell you that there are phenomena all around us, which can be understood in very simple terms, at least to a certain scale, to a certain level. And now, to most of you who are probably undergraduates, the idea is, now that you realize that you're surrounded by phenomena, which in this particular case, it is not only capillarity and elasticity, there was also evaporation and heat transfer, and Marangoni flows, which is difference in surface tension creating a flow, but the difference in surface tension can be created by difference in heat, by heating it up, or by evaporation, which is concentration differences. So all of these things come together to create this different phenomena. So this was the introductory lecture to let you know about these phenomena, and that there are simple ways with which we can probably understand some of it. And the next lecture, hopefully, would be about the history and the timeline of spreading. So with that, I'll end today's lecture. If you have questions, I'm obviously going to take them.
Maybe we can have a round of applause for Saurabh first. That'll be nice, yeah. And maybe we can all unmute ourselves.
Thank you.
I think there are a couple of questions on the chat. So if you go to the chat,
Okay.
so there is a question on what about the volume of the droplet? Does it have an effect?
Effect on what?
I think it's near the first part of your talk.
It was the question on the contact time of droplets impacting a super hydrophobic surface, and I think you mentioned because it depends on the radius of the drop. So
Yes, it depends on the radius of the drop. So it goes as a radius to about 3 hubs. And don't call me sir, call me Saurabh. The contact time is square root of m over k, like the characteristic time of any spring. And here I'll show you the experimental results. This is where you see this is the droplet radius. This is the contact time, and we see that it is unbelievably good. Over 2 decades, you see it follows radius to about 3 halves, and radius to about 3 halves essentially means, as I showed here, that if you write mass divided by k here is gamma, and mass is rho r cubed, so it becomes r to the power 3 halves. This is a log-log plot. On a log-log plot, this is a straight line, which means it follows a power law, which is r to the power 3 halves. I hope that answers your question. So it does depend on size. There is a, okay.
So there is another question on what's delta, the volume deformation. I think that's related to when you were trying
Yes,
to pick.
delta is the volume deformation. It can, we could have made delta is the volume deformation. Let me just put it like that. So I have kept it very simple over there as a linear spring. We can obviously go further into it because there's the delta, which is called the Hertz contact, scales as small r squared over capital R, small r being the contact size. But yes, it's just the volume deformation. Yes. Yes, the force is surface tension times length. You're absolutely right. So if I go here, this is what I'm proposing as, yeah. This is, of course, a more involved process. For instance, for water, I said that there is no viscous dissipation, but if you were to do the same experiment with more viscous liquids, then you would see that around 300 times the viscosity of water, the contact time becomes infinite. By that I mean that it just hits and deforms and sits like, and comes back and sits like that. And my lab mate is doing experiments on that, and he has shown this. All right. So when you showed, Onik has a question. When you showed the experiments of the paper wrapping on the bubble, it was a drop. Perhaps I should have specified it. You took the analogy of a simply supported beam, but when you see that, yes, it's so I showed a beam. I was showing actually a thin sheet, but yes, it also holds for a beam. In fact, the arguments also hold true for a beam. A beam would be the fiber, in which case also you find a very similar elastocapillary length argument. I hope that answered this question, because I was showing a sheet. Oh, where are you? I'm here. There you go. Yes. Okay, can I see the... Okay. Any other questions?
Okay, so Nath, in connection to the last question, there's another project that I'm working on. So if you think about a leaf and think about a raindrop hitting the leaf, that is a very common way how the spores which reside on the leaf surface, they spread out. So there we are actually more interested about what is the flow field like because of that impact and because of that oscillation of the beam and how that helps the transport process. So I just wanted to mention this to the students because so basically what you showed today is a glimpse into your research. And it might seem a little abstract to many folks at JU. It would have been abstract to us 10 years back, or in your case, 5 years back. But the thing is, many of the things that we are working on, they can be applied in other areas as well. So if you guys come to graduate school, do a PhD, you'll gradually realize that knowledge at the end of the day is convergent. Like you come from different disciplines, you are work on different research topics, but you can apply the tools, the knowledge that we are developing in other different areas. And in Nath's case, the kind of problems that he showed can be applied in many other cases as well. So just be open towards that kind of applications.
Yeah, I largely agree with everything that Shrikota has said. I have not yet shown my research though. This is broadly the research of soft matter physics. Much of it is from different people I know and the things that I was interested in. But regarding applications, which is very curious, we want surfaces with lower and lower adhesion for a very particular reason. One of those was the heat transfer, which I showed, which is when you have a molten tin drop and there's a possibility of solidification. For instance, when you have an airplane flying through clouds, the droplets inside clouds are actually super cooled and they impact on the airplane wings and they freeze immediately. But if you can somehow rebound them off very quickly by creating a surface which is very repellent, then that's very helpful. There's also more. For instance, now that you guys are wearing masks and when you wear specs, you must have noticed that your glasses fog very quickly. But if you have a surface which is anti-fogging or water repellent in some sense, like a super hydrophobic surface, then these droplets would be repelled very quickly. I did not go into the details of what a low adhesion surface is or how a super hydrophobic surface functions, because I wanted to give you just an overview of different kinds of very cute little phenomena that happen with super hydrophobic surfaces in part of this system. But of course, it has tremendous applications everywhere. Another application would be, for instance, in condensers, where you want a lot of heat transfer to happen. What happens is when you have hot steam hitting a plate, it forms a thin film. And so later on, the steam does not come in contact with the plate anymore. And that creates a huge thermal resistance. But if it's a super hydrophobic surface, then the steam would condense and then roll off immediately. And so it'll always keep coming in contact with with this uh, with this plate. And that is, of course, very helpful. The problem with this is that superhydrophobic surfaces are not robust, and that is where research is stuck right now. But that's a problem of chemistry, which is beyond my expertise. But as far as physics is concerned, we can of course dabble in the different kinds of things which happen on superhydrophobic surfaces. And one of those is showing that the contact time is independent of velocity, or it's very low. And just by approximating it as linear springs, you can actually find out quite a lot of things. So the next talk is going to be by Shoykot Basu, who is right here, who is an assistant professor in South Dakota State University. And he's going to talk about biomedical fluidics. His talk is called Fluid Mechanics as a Tool of Medical Diagnostics, if I'm not wrong.
Medical science.
Medical sciences.
But medical science itself is a huge term, so we will have to qualify what I mean by medical science.
Yeah, so of course he's way more qualified than me. I have no idea about any of this, and I'm very excited to hear what he's going to tell us, because this will be the first time I will hear about biomedical fluidics. I've heard of biofluidics.
By the way, that term was made by you, not by me. Biomedical. I have never heard of that term either. Biomedical fluidics.
Yeah, well, now it is in vogue now. Because I've heard biofluidics and I've heard fluid mechanics of medical sciences, but now it seems like it's time we have something.
You are the one who started this term, biomedical fluidics.
I think it's quite apt, but I would love to hear more tomorrow, which would be at 7:30 p.m. here, Indian Standard Time.
Right. Now, Nath, would you like to give a bit more insight into why we are doing this?
So, as I said in the very beginning, which was primarily the kind of the manifesto of the Vanguard. So we four have come together to essentially provide people who don't have physical or social capital with access. So these lectures are going to be there, always available for you. And this is only the first one. And after this, it will be followed up by lectures of the rest of the three of us. And then I would do the second in this series. And we would continue up until you say that, oh, there's enough, or we feel that I think this in itself forms a set. So in line with how the Nicholas Bourbaki functioned, who used to be a group of people from ENS, students from ENS, who anonymously wrote a bunch of books and rewrote the entirety of mathematics. We don't intend to rewrite everything which has been done in soft matter physics, so to speak. But what we do intend to is provide social capital and access to research to everyone who does not have capital. And that is what we're doing here. So we start that. The first stepping stone towards that is this series of lectures. The first introductory lecture was this one, which is just an introduction and a series of phenomena. And the next one is going to be an introduction to what Shoykot is going to tell you about regarding biomedical fluidics. And after that, active matter, and then that will be followed up by pattern formation, which will be given by Shoykot Mukherjee. And I hope that this can help in creating a cohesive unit and in some sense provide us with the capital that we don't have yet.
Can you guys see my screen?
Yeah, I can. I'm glad you pulled them up.
Okay. So this is you can just see my screen, right, with the picture?
Yeah.
Yeah, so this is the group that Saurabh is talking about. So they founded the so-called secret organization in the 1930s. They wrote a number of textbooks. One reason why they did that is has its backdrop in the First World War as well. So during the First World War, as we know, it took out a large chunk of the French younger population. And that included a host of mathematicians and physicists and engineers. And they realized that whoever is left in that community, they were lacking in access to good quality text material. And as a result, their research quality is suffering some setback. So they came up with the idea that we should collaborate to write textbooks, new textbooks, to collaborate on publishing new papers, new research papers, and many of them were quite famous in their own rights. But they wrote the textbooks, and some of those books are still being used. They wrote the papers under the common name, which is Nicolas Bourbaki. So this is a French general from the 1800s, and they chose the name just because they were trying to sort of inculcate that same flavor in their work. So we are trying to recreate a similar kind of fervor. Of course, it's a different world, it's a different time, but we still have a number of obstacles. And the way Bengali science has suffered in the last 50 years, if you take a time machine and go to the 1950s, 60s, 70s Kolkata, it was a vital Kolkata. I mean, not only in terms of science, in terms of arts, literature, everything. I personally feel that is lacking right now. And I would still like to believe that we have enough talents among ourselves to coordinate amongst ourselves and collaborate to generate something that will stay. I mean, things have to stay beyond us. And right now, the quality of work that is being done probably is not that time pervasive. And I'll talk more about these things and also about my research tomorrow.
A lot of this has to do with capital, and what we can definitely do is reach out to you, and that's the first step. And then we'll see how this develops over time. And I think now we can. I mean, we would. I would love to hear more from you guys who are here. So if you guys have any questions or anything, like if you think that, oh, this presentation was absolutely horrible, unwatchable, then you should also come up and say that. Or if you think that it was not completely crap, then you should you can also say that.
Yeah, by the way, Saurabh, you have a book on your background, Argumentative Indian. So
Yeah.
it is definitely important that we do argue. So I would encourage the students to argue with Saurabh as well. Any questions? You guys can actually speak out and not just write on the chat line.
Well, it appears that they're quite content. Or um, I would also like to acknowledge Ananda, who has done a lot of the heavy lifting, without whom none of this would have happened. So thanks, Ananda.
Broto, do you like to share something?
I think no, that's. I think you have both of you have shared what I thought. So it's perfect. Nothing more to add right now, at least. I mean, one thing that I think I don't know whether we have done it already. That we were thinking of preparing a feedback form where you can write suggestions. And so while there is, like Saurabh said, that we do plan to extend certain topics that you like over here, maybe to next lectures and other lectures. But if there are topics that you would like to hear us talk or someone else talk, then we can try to organize that as well. So that's something that we are open about, and we'd like to hear your suggestions.
It's
Feedback is
Shrekat
very.
here? I don't think Shrekat joined the call. Shrekat Mukherjee.
I think he's not here.
Something should be here.
Yeah, I've seen water is slippery on surface, but adding some drops water and rubbing on my foot makes a hindrance. Why? Water. So now Devjit has sent me a direct message which says that water is slippery on surface. Okay, first of all, whether a water drop is slippery on a surface or not, it depends on the kind of surface you have. So super hydrophobic surface is one kind of surface where water is slippery. So which is what you saw here. Let me show you this particular video which I skipped. So on the left hand side you see a super hydrophobic surface where the droplet becomes as big as 3 millimeters and then leaves. But on the right hand side, there's a regular surface where you see the droplet is gigantic and it will become as big as 30 microliters. And you see that when it detaches, because both are under action of gravity, there's a huge difference between the contact angle in the front and the back. This is called hysteresis. Hysteresis is the difference between the cosine of the advancing angle and the receding angle. On a superhydrophobic surface, what happens? So first of all, why is there this hysteresis? The solid surface has a lot of asperities and the droplet gets pinned on these, and that's why you can see these different angles that are possible. But on a superhydrophobic surface, the droplet sits on top of a thin air layer which exists between the texture, because there is texture on a superhydrophobic surface. If you chemically, a surface can only go as large as 120 degrees. If you want to make it any more super hydrophobic, any more hydrophobic, then you have to add texture to it. How that functions is something that I can talk later in detail about. But what this eventually does is it makes the advancing and the receding angle the same, which is what you'll see here when it detaches. The advancing and the receding angle are not very different, which means that it had, and the force resisting its motion is surface tension times cosine of the advancing angle minus cosine of the receding angle. And so one can say that the droplets are very slippery on this because it has very little lateral adhesion, as you can see. If you had a little bit of oil on top of the surface, it would be slippery again, but that would be for a different reason. That would be because all the asperities will be eaten up and covered by a thin layer of oil. However, your question as to why it is difficult for you to walk when you have water under your feet, it probably is due to the, well, you can still slip and fall. Uh, well, it probably is because of lubrication pressure, but I find the question slightly ill-defined. If you can define it a bit better, then probably I can answer it more. So you're saying rubbing my foot makes a hindrance. Adding some drops water and rubbing water on regular. I mean, I would imagine that if you have a little bit of a thin film of water on your regular floor and you're trying to walk, you'll slip and fall. It'll decrease the friction. It can increase the friction if it is not water but a viscous liquid. I presume that we're comparing it in comparison to you just trying to laterally move your foot on the surface. I hope that answers the question.
Nath, I don't think it's lubrication pressure. Think about the time scale, and it's something much more mundane. It's not that sophisticated.
So, I mean, if you're okay, he's saying, could you also explain the carbon suit layer? Yeah. So, look, first to answer your question, I think that if there's a little, so if there's a little thin film of water and you're trying to walk on it or you slip and fall, that's called hydroplaning. That's because okay, so this is a different kind of thing. It is like this. So there is a classical experiment which is called the Landau-Levitch experiment, where you have where you have a plate and you draw the plate out of a beaker full of water. So imagine here is a beaker full of water and you draw this plate out. As you draw the plate out, it also draws a thin film, a layer of thin film on this surface, and this thickness of this film depends on the velocity at which you pull it, and the more the velocity, the more you pull it. Now, when someone slips on a surface, or when tires skid on a road with a thin film of water, when they hydroplane essentially, they do the same thing because with the velocity with which they are rolling or with which it's moving, it also draws in more liquid and lubricates it, and that's which is essentially like drawing this very quickly. This is the Landau-Levitch principle, which also follows over there, and it has been shown that the thickness of this film goes as capillary number to about 2/3. So, and even when you have droplets sliding over a surface with thin film of oil, the faster the droplet goes when it starts rolling, it draws in more and more oil, and the thickness of oil beneath the droplet increases. So this was shown 3 years ago by Joanna Eisenberg in an article in Nature Physics called oleoplaning, which was slipping on oil, and simultaneously by my advisor in a soft matter paper, which is called drop friction on liquid infused surfaces, which are all different variations on the same theme of aquaplaning or hydroplaning or oleoplaning, where you have this Landau-Levitch principle. We'll also cover Landau-Levitch someday. Now, Devjit has another, Ornov Paul has a question. How can you explain the carbon suit layer you made and the polymer you showed are similar? So I'll not go into the chemistry because chemistry is not my strong suit. What I can tell you is that, no pun intended, but this is a strong suit. As in, like, if you make a carbon suit layer here, it functions in a double way. I'll tell you how. So if you have a super hydrophobic surface and you deposit a water, it just sits on top of it like a pearl. There's another way to do this, which I did not show, which is called the liquid marble. So suppose you have you probably have noticed this, that if we have a lot of dust somewhere and you put a droplet, then the dust coats the droplet and it becomes spherical. So that is called a liquid marble. Now the particles which have to be used to coat this drop are hydrophobic particles, which are called lycopodium. Sometimes when you use talcum powder, but like talcum powder which has not absorbed water, because talcum powder has the propensity to absorb water, that's why you use it under your armpits. If you have dry talcum powder, it functions in a very similar way. And again, another experiment very frugally you can do at your home. But definitely you can do it with dust. It always works with dust. And with lycopodium, it's perfect. You will get very reproducible results. When the suit on this is very fragile, so when I just deposit a drop, I don't know how much this is visible. This drop, there you go. It quickly transitions because the suit is very loose. So maybe I'll try once more. So here, this bounce that you see, this bounce happens because the suit functions as a thin monolayer which is sufficient to create superhydrophobicity, but because it is loose, the drop also takes it with it. So it becomes a liquid marble for some time. But of course, I have not completely coated it. But if I had coated, then you would have seen that the droplet sits with these particles. So for instance, when Shoikota was talking about spores on a drop, so for instance, wheat leaves are super hydrophobic and they have spores in it also. So when droplets bounce on them or raindrops fall and splash on them, they take these spores and they are coated with it. And these spores are hydrophobic. They are just like carbon soup particles or lycopodium particles, and they're surrounded by it. So I hope that answers part of your question. But I've seen mopping the floor at the end. It's so Devjit says that when he's mopping the floor and there is not enough water, the friction, or when he's walking on the floor and there's not enough water, the friction apparently increases near the end. So the friction increases near the end in comparison to in the beginning. I guess that's what he's trying to say. And if that is what you're trying to say, then I can say very, very naively, if I were to propose that the viscous force is the friction force, the viscous stress goes as eta V divided by H, H being the thickness of the film, then near the end, when the film thickness is very low, then your viscous force should increase. However, throughout this, whatever dissipation you have is it's going to be lesser than what you have when there is solid-solid friction, where actually you don't have solid friction, you actually have uh, friction because of elastic deformation, which you have between, say, two rubbers, which is more complex.
Yes, Saurabh, so in that connection, let me propose a possible project. So you said that uh, slipping or hydroplaning happens when there is this rolling motion, right?
Yeah.
And from our personal experiences, we know that some people are more prone to slipping than the rest. So it can be correlated to the walking style as well. And we know from a common experience that when we see that a surface is slippery, you tend to apply your foot more vertically than your regular walking style. So is it possible to basically record the walking posture to figure out what is that rolling motion that is going on, and hence detect people who would be prone to more sleeping. So this can be a subdiscipline that can be of interest to the orthopedic surgeons and that area of medical science. But I think there is an open problem over there where you can actually apply that physical thing that you are studying, and then apply it to how it can affect us in real life.
I think it is possible, and I can also think of an experimental design to do this. What has to be done is you need a glass platform on which a person with a thin film of water on which a person needs to walk,
Yeah,
and from the bottom you need to take an image where the lit up in a certain way from the side so that you can have some interferometry images, which will tell you the thickness of layer as the person walks.
yeah,
So for instance, in the experiments that I told you, which Joanna Eisenberg has done in this article, you will see they used a glass plate, and they were trying to do interferometry from by bottom up microscopy. You don't need a microscope to do interferometry. You just need a camera, and you just need proper lighting, and then you can do interferometry. If you do interferometry, then you will know um, film thickness and how it changes, and that will tell you more. For instance, if there's one person who is walking at different speeds, and the initial condition is always the same, but the thickness of the water film is constant,
yeah,
then what can be seen is that how that thickness changes with his walking speed, and probably there is a critical transition somewhere, and where he finds it much more difficult, or he slips, or he falls. Now this transition itself can be plotted with respect to different people who have different styles of walking. Now I don't know what that section is,
yeah.
but
So gait analysis is a very common. It is an established area of research. So people have been studying gait dynamics for the last 30, 40 years. I think the first major paper came out in 1982. They made people walk on treadmill. They're still using similar kind of observational techniques, just that the imaging modalities are much better now than in the 80s, so they can gather a lot of data about the gait dynamics. And I think it has to do with the topology of the foot. So I think there is a potential problem out there. I would like to share my screen once again in connection to your comment about wheat leaves. So this might be of some interest to the folks here. So I think Nath was talking about wheat leaves and how they act almost like a beam. And if there's a drop impacting on the wheat leaf, uh, we would see similar kind of mechanics. So this is the other project that I am part of. It's a collaboration with other schools. So yeah, we are trying to recreate the wheat leaf mechanics by a simple beam. And this snapshots on the right, they did some PIV, and they're looking at the flow structures that are being generated owing to the drop impact and owing to the oscillation of the beam. So it's a very interesting area. Yeah.
Mhm. It is. It is. When I was in Virginia Tech, I was doing a project on it, and there's a lot of work happening in this domain, which is plant pathology and fluid mechanics, the combination of the two. And Sunny has obviously done some work on it, and which you
Yeah. So
definitely do.
this is a collaboration with yeah, Sunny student.
Yeah. So yeah, there's a lot of interesting stuff that can be done here. My work was not on splash though; it was on jumping, but it's similar. It's a dispersal of spores from leaves to other places through droplets. That's what it was, and I think it's a quite it's a ripe area to do a lot of stuff. All right, so I see that our audience have been pretty silent. Uh, I also see Brotoda smiling a lot.
Okay, I think we can stop the recording now, and
Yeah, I think we can
all of
definitely
us
stop
should
the recording.
chat amongst ourselves. And thank you guys for joining this, and we are going to see you tomorrow.
Thank you, everyone.